Okay.
You're making another video, or just?
Yeah, I'm making another video, I think. I don't know. We'll find out. Okay, so here's what we did. 3 seconds, plus or minus a tenth of a second. Lots of other experiments would probably have to be performed, but let's just analyze this. The next step was to calculate the launch speed of the rocket using that. So that was using the following equation. Average time, so 3 seconds, times acceleration due to gravity, divided by -2. That was that whole initial and final same number, opposite direction thing. Okay? So if I do this, equals 14.7, or with 2 sig figs, 15 meters per second.
Wait,
Now,
are we in yards right now?
are we in?
We're in yards currently, aren't
We're in meters right now. We're going to convert to yards at the end.
we? I thought we were in yards, we had to convert to meters.
Nope. Did you use 9.8 in your calculations?
Yeah.
That's meters. It's fine. So notice I put a plus minus value here. Because we had a confidence limit for the time, which we used experimentally here in this calculation, we have to drag this along. So what should this be? Charlie? That's all right. Go ahead.
So are you going to keep 2 sig figs for the rest of it?
Yes, that is correct. Liam? Why 0.49?
Because you put it through the same equation. You put it in place of the 3 seconds. So that's how you find the confidence.
That is correct. You have to put the confidence limit through the same calculation. Now, I usually do it twice. And it's because most of the time, if I just put the 0.1 right here, it would be fine. However, sometimes you have rounding issues, like round up, round down. So it's better to actually run it through twice. Let me show you. The maximum time using this confidence limit would be 3.1. So I'm going to just redo the calculation. And I get 15.2. And then I'm going to do a minimum, 2.9 seconds. And I get 14.2. Now, since I rounded this to 15, what plus or minus value should I use here to make sure that it encompasses or includes both of these? So, yeah, 1 meter per second would be fine. You can take an extra decimal place when using confidence limits. That's kind of your judgment call. If I wanted to use plus or minus 1, that would be fine. That would get us to 16 and 14, which would include both of those. You could go 1 more decimal place and do 0.8. So either of those I would accept. Okay? So you see how 0.8 gets you down to 14.2, but it goes way beyond 15.2. You just have to make sure you include both. Or 1. Either of those would be fine. Okay? So let's keep going. So this is why it's kind of a pain if you had to do this and type it all out. So this would be done in the field. Then you would take this data and analyze it. This is still raw data. And then the final results go in your pretty final typed up report. Go ahead.
Would you be able to do +2 and minus, or +0.2 and -0.8?
No, that's not usually. That would be correct. But the standard is to have one confidence limit that encompasses both maximum and minimum. That's a great question. Okay. Next step was to calculate time in the air when the rocket is launched at an angle. So time, this is more analysis, was equal to -2 times the initial velocity, which we calculated to be 15 meters per second, times the sine of, and let's say this was a 55-degree wedge, so that would be a 35-degree angle, By the way, if any of you did that extra credit where you found out why the complement worked as the launch angle, you can show me that. And then we're going to divide by gravity. So that equals...
How did you get theta?
I had a 55-degree wedge. And remember I said that the launch angle was the complement to whatever was on the wedge.
So is that like all for all of us, it's 35?
No. What was the angle on your wedge that you stuck in?
And your wedge is 7.
So for you, 35. Maybe somebody else had a 30-degree wedge, so their angle would be 60. Make sense? Okay. All right, so when I do this, for 2 sig figs, I get 1.8 seconds. Right? But, of course, there's a confidence limit. So again, I'm going to do time max, time min, using my confidence limit values here. So these are constants. That's just based on the angle. So this is the only one that's going to change. And if I look back, remember I said it'll be plus or minus 0.8 or 1. Which one do you want to use? Okay, so we'll use this one. So the maximum would be 15.8 times the sine of 35 degrees divided by negative 9.8.
Why would you use the?
Because that was our confidence limit from this step right here that we did.
Can you go over how you, why do you take 0.8 and 5?
Okay. Remember that here we had an average of 3 seconds in the air, give or take 1/10 of a second because of human reaction time pushing the button on your phone, right? And so I carried that confidence limit here and here. So I did the same calculation with a maximum value. So it was 3 seconds, right? Could it have been 3.1 reasonably? Yes. Could it have been 2.9 reasonably? Yes. So that's why I ended up actually having to do this calculation 3 times. Now, by the way, if you're grooving on this, you're like, oh, I can't wait to see what happens in the end, you might want to consider scientific research. It does help when you care about it. Like when you really want to know if the little fish are being stressed out because of evolutionary, design, or because of pheromones, or because they have fishy Parkinson's disease. So it does help if you care. But if this kind of gets you excited, then this is what research is all about. If, on the other hand, you're like, what the hell, I don't even care, then just do it because I said so you can get an A, and then maybe perhaps choose a different career. Charlie?
Okay, so that explains why you added the 0.1.
Correct.
Why you added, I don't know.
All right. So then when I added the point and took away the 0.1, right here and here, right?
Yeah.
I got 15.2 and 14.2. So that confidence limit carried through to this velocity. So with reasonable results of plus and minus 0.1, I could have up to 15.2 meters per second or as slow as 14.2 meters per second.
Okay, so since that was 0.8 from the original, that's the one you used?
Yes,
Then why did you use 0.2 then?
because 0.8 includes 0.2. I'm trying to include both the maximum and minimum results.
So it's like the time average is always going to be 0.1.
Yes,
Okay.
because we decided that was human reaction time. Yep.
So do you always take the minimum?
No, you take whatever the biggest delta value is. Anybody know what I'm talking about there?
Change.
Yes.
Triangle thing.
Yes, that is correct. All right, so now you know where the 15.8 came from, right? So what we're doing is we're carrying that 1/10 of a second through every single calculation. So here we go. So 2 times 15.8 times the sine of 35 degrees divided by 9.8 equal, oh, what did I do?
Negative 9.
Oh, probably. My bad. Make sure your calculators are in degrees and not radians when you do these. And I got 1.85. I'm going to keep an extra sig fig around just to see what happens. And this would be minus 0.8. So what number value would go here for the velocity? 14.2. And I get 1.66. So, now back up top. Time in the air when we shot it in an angle, 1.8 seconds, give or take how much to include both of these?
0.13.
Yeah, this rounds up to 1.9, this rounds up to 1.7. 0.1 would probably encompass both, that would be fine. This does get into where you have sort of a, are you going with an extra sig fig for your confidence limits? Are you staying in the 10th place? As long as you're consistent and as long as you show these results. So if someone were trying to reproduce your experiment, they would be able to look at this and that's where they kept track of their confidence limits. So a 1/10 of a second would be completely reasonable here. Okay? Because this rounds up to 1.9 and 1.7. Does that make sense? Yeah. This is 2 sig figs. This is the most correct.
I know, but 0.1 only gets you 0.7, 0.8. Oh.
Thank you. Okay. Last step, find the distance. Distance equals velocity times time. So that's 15 cosine 35. We're doing the horizontal times the time in the air, which was 1.8 seconds. You see why we only do one of these per marking period. And, come on, Mystic. This is just the raw data. 22 meters. Then I'll do distance max, distance min. Oh, but there's something special here. I not only have one, I have 2 experimentally calculated data points. Because that's the velocity and that's the time in the air, right? Here's what you do.
You just do the max and
Don't ever do this. Does that make sense? Do max max, min min, and you will capture all of the values. You don't want to have a negating effect by doing maximum and minimum. You don't have to do it 4 times, in other words. Okay? So the 15 was plus or minus 0.8, right? So maximum would be 15.8 cosine 35. And the 1.8 was plus or minus 1/10, so maximum there would be 1.9. Very good. So 15.8 cosine 35 times 1.9 equals 24.6. So 25. And now we're going to go minimum, so 14.2. Time would be 1.7. And I get 19 points out, about 20. So what plus or minus value would I choose to encompass both the maximum and the minimum?
3.
3. Good. Now we're almost to the finish line. Almost. The horizontal distance on the football field was not in meters, so Wes, this is our yards adjustment. So 22 meters, 3.3 feet in a meter. 1 yard is 3 feet, and we get 24 yards, give or take. Let's do our 3 value, right? 3 meters is how many yards? Okay. There we go. So all that work, so that you know, when I shoot the rocket, it should go, based on our limitations just from reaction time, somewhere between 21 to 27 yards. If it lands within that sweet spot, whee, your results come out as predicted, as anticipated. Now, there's another little problem here. Within the scientific community, research needs to be reproducible, and it needs to be within acceptable limits. And those acceptable limits are typically 5% confidence limit or less. 10%, so 5 to 10%, usually means it warrants some more experiments. How's that?
That's way more than 5%.
Way more than 5, and even a little more than 10.
No.
Fail. But remember, you were just doing this for an hour, right? If you were truly doing scientific research, this would warrant probably fixing some of those things like hitting birds and askew nose cones and wind and all that kind of stuff. All right. Hey, we just talked for a whole hour about one set of calculations. So was anybody during this discussion like fascinated, like, wow, research sounds cool? Or did you get to the finish line and you were like, oh my Lord, kill me now?
It depends what we're talking
A little bit of
about.
both? Yeah. Yeah.
If we were talking about like little fish having seizures, then I was like, oh my God, kill me. But if we're talking about something like significant, I'd be like,
Fish having seizures could cure Parkinson's someday. You never know. Did you miss the sticky notes? Go ahead. Sure. Here's what I'd like you to do tonight. This is due next Friday. So you've got a lot of time to work on this. I want you to re-look at 3E number 4 or anything from 3E because that was actually a hard section.
it was.
There were 2 unknowns. Look over here real quick. You were given the horizontal distance and you didn't know velocity or time. So you need to sort of look at the toolbox, and I'll give you a hint. You need to combine or substitute 2 equations to solve this. So if you didn't get 3E number 4 on your own, I want you to revisit that tonight.
Wait, you don't have to start with 4A.
No, we haven't actually gotten to this. I'm going to shift this down. We'll still do Fun Fact Friday, but I think I'm going to reschedule the lab for either Tuesday or Thursday, one of the in-between days. Nope, you got thrown me. I know, all that evidence. Well, take 3 and draw it. Sure, but. I need, like, an electroshock.
We would have been 5.
Maybe I'm not pronouncing, you know this.
Wait.
I need, like,
The complement of the wedge was 35.
okay, well, I'm sorry.
So the wedge was 55. So we used 35 in our 55.
Procedure is fine.
The wedge was 55.
You're fine.
No, the light was 0.72. I would have never done that.
Yes.
Anyway,
I did this while I was
we
lecturing.
added
Kept on. We're out of. Oh, got it. Okay. Yeah. So this would be raw data, and that's fine. Well, data analysis is what you're doing. The raw data technically and data analysis. And then at the end, you would kind of put that finish line data, so that's really complicated. Sorry, I don't know if it's like
you can let you.
Yeah.